The magnetic field within a solenoid. The figure is a model of a solenoid. It shows magnetic field lines as well as an Amperian loop, which is labeled ABCD. So you can see that it's a little bit of a rectangle here, ABCD, there's an Amperian loop. And we're going to use this to derive the equation for the magnetic field inside an ideal solenoid. But first, a bit of information, and then let's go through a handy right-hand rule for solenoids. When current flows through the insulated wire wrappings of a solenoid, they have to be insulated in order to force the current to continually go in successive loops. If that wire is not insulated, the current will just skip across from one loop to the next, and it won't actually go around in a helical path, which is what we need. So those wires that make up solenoids are typically insulated. When current flows through the insulated wire wrappings of a solenoid, the solenoid itself becomes a temporary magnet, with one end of the coil becoming the north pole and the other becoming the south pole. Now, which pole is which? Well, that's what we use our right-hand rule for solenoids for. And it says, let the fingers of your right hand point and curl in the direction of the conventional current as it winds around and around the central core of the device. Then your right thumb will point towards the north pole end of the solenoid. Let's see if we can show you that. In our figure here, which end of the solenoid is the north pole? So we got to get your right hand out here. You need to let your fingers curl in the direction around the center that the current is traveling. And if you can look at this diagram, you can see that the current is closer to us now, and then it goes to the back of the solenoid. Now it's coming towards us, now it's going away from us, and so on. Watch my top fingers here where my fingernails are. It's coming towards us up here, and then it's going away from us down there, and my right thumb is pointing to the right. So that's going to be the north pole of this temporary magnet. We're now going to derive the equation for the magnetic field inside an ideal solenoid using Ampere's law. Note, in the figure, there's a current I in the wire. The solenoid has a length of L, and there are N loops of wire. We're wrapping this around N times. The Amperian loop, which we mentioned earlier, was ABCD, shown in dashed lines. Once again, that's the rectangle right there. That's our Amperian loop. This is the one case that we're going to run into where the Amperian loop is not a circle. Note also that the coiled wire pokes through the bubble membrane of the Amperian loop one time per winding. You can see that our Amperian loop, this wire right here where I'm pointing, is coming towards us. So that current is poking towards us. Then the next winding, that current is poking towards us, etc. We need to keep that in mind as we proceed here. So we're going to start by writing the equation of Ampere's law, which we've written a bunch of times already in these videos. But there it is. Since each of the N coils pokes through the membrane of the Amperian loop, and since each poke through carries a current I, the total I enclosed is N times I. That quantity right there is going to end up for I enclosed. So far, so good. Now we need to do a little rationalizing here with regard to this ideal solenoid. The part C answer takes care of the left side of Ampere's law. We just said that the enclosed current is N times I. On the right side, we recall that up to now, all Amperian loops have been circles. This was because our magnetic field needed a constant value along each DL segment around the loop's edge. For a solenoid, though, the magnetic field cannot be constant for any reasonably shaped Amperian loop. We weasel out of this by using a rectangular loop and assuming an ideal solenoid. Unlike the real solenoid in the figure, an ideal solenoid has magnetic field lines that go straight for a very long distance along the solenoid's axis once they get outside the solenoid. Then way far away axially. They finally curve back around, swinging wide to a very far radial distance away, thus completing their continuous loops. All right, within the solenoid, the magnetic field is constant. So, assuming an ideal solenoid, we're going to flesh out the right side of the equation. So the right side of the equation, we're going to end up doing this little b dot dl integral for each of the 4 segments of this Amperian loop. For which of these 2 terms that are shown, so this is the right side of the equation that we've broken into pieces, which of those terms will be 0 because the magnetic field and the dl bits are perpendicular to each other? What we're assuming here, and again, this is not what the diagram shows, but we're assuming that when we're outside the solenoid, these field lines, like this one here, and that one right there, and that one right there, they are a very far radial distance away, and they're all parallel. So basically, through the AB segment and the CD segment, right there, B and DL are perpendicular. And also for the CD segment, perpendicular for both of those. So those go to 0 because the dot product of 2 vectors that are perpendicular is 0. Now, which one term will be 0 because there's no magnetic field along that edge? Well, that's going to be AD. That one's going to be 0 because, once again, we're assuming that these magnetic field lines, they go way far axially, all right, way off the page. I can't even show it. And then they swing way wide, and finally they come back in like this. So right along AD, there is no B field. That's what we're assuming. So the only one that's left is this guy right here. We're going to integrate along right there. And what's that going to equal? Well, that's going to equal the magnetic field, dot product it with each little dl bit. Well, if B is constant and you integrate that, you just get L. So the right side turns into simply BL. The left side from the previous page was mu naught Ni, and the right side is BL. So what's the equation for the magnetic field? Mu naught Ni over L. That's the equation for the magnetic field inside an ideal solenoid. Finally, last important point on solenoids. Inside, the magnetic field is constant. Outside, it's not equal to 0. We're not really interested in what it is usually, but it's not equal to 0. But inside, it's constant. Doesn't matter if we're right along the axis of the solenoid, or if we're near the top within those coils, or if we're near the bottom or halfway in between. It doesn't matter. Inside those coils, the magnetic field is constant.